So I had started by saying wetting is just the phenomenon of getting a solid surface wet, like getting it filled with water. So one of the most interest pharmaceutically is the behavior of a liquid in contact with a solid. So sorry, what I've said, actually, I've said that wetting is the process of making a solid what drenched with water. So it's not water, rather it's the phenomenon of liquid coming into contact with a solid. So this phenomenon of wetting can be described by different properties, which we'll be going through in this presentation. So the first property will be contact angle. So if a drop of liquid, at least in most of the examples I'm going to use water, is placed on a flat, smooth, horizontal solid surface, it may spread completely, but it's more likely to form a drop. Like for example, when you're in class and then you drink water and then like a droplet of water falls on your desk, for the most part, you'd see the water forming spheres. If it's like a small amount of water, if it's a lot of water, it will drip. But usually water leaves behind the spheres and all that. So all of this is because there's gonna be a definite angle against the solid, and this angle is what is called a contact angle. So we're assuming this over here, this line over here would be the desk, and then on top of the desk there's air, and then what is formed over here is the water droplet. So you see where the water droplet is coming into contact with your solid, which will be your desk, there's an angle over here, and this is what we'll call the contact angle. So by equating the horizontal component of various interfacial tensions, the following equation is derived. So the equations are rather long, and I'll just read them as is because I don't know how else to explain the equations more simply. So this Y, as we know, it stands for surface tension. S over V is equals to the surface tension, S over L plus the surface tension, L over V, cos theta, and the theta is what I'm saying is the contact angle. Okay. So the S is the solid, the L is the liquid, the L is the liquid. I'm not sure what the V is. So the work of adhesion between the solid and the liquid is given by this formula. So when you combine this formula plus this formula, what you're left with is this one. So basically all these three formulas, after being combined, what it means is that the work of adhesion between solid and liquid can be determined in terms of measurable quantities. Remember, in order for wetting to happen, there is cohesive forces and adhesive forces. So if it forms a sphere, from what I said in the morning, it means the cohesive forces between the liquid are stronger, and also the cohesive forces between the solid are stronger. So instead of the liquid spreading completely and forming a layer, it will form a sphere. So in a similar manner to liquids, a spreading coefficient for a liquid on a solid may be defined as using this formula. This gives a measure of how well a liquid will spread on a solid. That's what I was explaining. So if a liquid is penetrating into a capillary, for instance, the pores in a tablet, the value of interest is the adhesion tension. So adhesion, what we said in the morning, it's the forces between two molecules which are similar. So again, it's given by this complex formula. So since this surface tension of the L over V is always positive, the spontaneity of these processes will be controlled by the cos theta, which is the contact angle. So for example, during penetration into capillaries under no extra applied pressure, the adhesion tension must be positive. Hence, cos theta must be positive. Remember when I said that if the tension is positive, that would mean like the adhesion tension is positive. It means like the forces between the liquid and the solid, it means that the adhesive forces are stronger. In the morning, I was explaining that if the adhesive forces are stronger when you're pouring one liquid over another, it means that there's going to be a film formed. If the if this adhesion tension is negative, like when we said, like sometimes like their components after they saturate, it's gonna be positive. Then when both of them saturate, it becomes negative, and then it forms the spheres. That's what I'm trying to explain from this. So the determination of contact angles for materials that are available as flat, smooth, solid surfaces is relatively straightforward. So a drop of liquid is placed on the surface, and the angle it makes with the surface can be measured directly by magnifying the drop in some way. So that was what I was trying to explain. Like if you drop water on your desk, then you're gonna get an outward angle, because if you magnify it, you can find that angle. But unfortunately, that is an ideal situation. In the real situations, most of the materials of pharmaceutical interest are powder, and such direct measurements on individual particles is not possible. So direct measurement can be achieved by compressing the powder into a compact. I think we learned that like with Calvin. Yeah, when we were talking about I think the dyeing machines, they were saying if you compact a powder, then it's easier for you to make measurements on it. It becomes the particles become closer together or something of the sort. So an HE method uses a compact but prepared at a lower pressure and saturated with the test liquid. A liquid drop is then formed on the surface of the saturated compact, and the maximum height of the drop is related to the contact angle. So what I'm understanding is, what I understood rather, is that when you have a powder, you compress it together, and then you prepare it at a lower pressure, and then you mix it with a test liquid until it's saturated. So then a liquid drop will be formed, but it's going to be formed from the powder. So it's like you're still able to calculate the contact angle. So you can't get the contact angle without mixing the powder with a liquid. So the other method utilizes a compact as dynamic contact angle analysis. Here, the powder is compressed into a thin rectangular plate, and the method used is the same as the Wilhelmy plate method for measuring the surface tension. I think in the morning I explained that that plate method was the one that I was not able to understand. So I can't, unfortunately, I'm not able to relate it even right now because I've still not figured it out. So to determine the contact angle of a powder without compacting it, the wash burn method is used. So here there's gonna be a powder bed formed in a tube fitted with a sintered glass filter at the base. So assume there's there's a tube which has a glass filter hapo chini. At the base is just the lowest point of that tube. So the base of the tube is immersed in liquid, and the liquid will penetrate into the capillaries between the powdered particles. So the rate of penetration is measured, and if the capillaries in the powder bed are regarded as being a bundle of capillary tubes, the rate of penetration is expressed using this formula. So L squared over T is equals to surface tension cos theta R over 2N. So L will be the length. So remember we said there's a tube. The tube, obviously, it has a length. Yeah, over T. T will be the time taken for the penetration to happen. And then cos theta is the contact angle, and the N is the liquid viscosity. So basically, you just need to input this calculation, and then you're able to determine contact angle without compacting the powder. So L squared over T is measured in the experiment. The liquid characteristics are known or can easily be measured. So the problem usually is determining the radius of the capillaries, because the capillaries are really small. So calculating okay, I'm assuming that that is what is going to bring the problem. So you can solve this problem by measuring the rate of penetration into a powder in an identical state of packing using a liquid that has zero contact angle against the powder. This is important because if the liquid has its own zero contact angle, it means either the contact angle is gonna be increased and you're gonna have like a slightly higher value or perhaps a lower value than you intended to find it. So substituting this into an equation will then give us a value for R, which can then be determined to can be used to determine the value of theta. So what I'm getting is you have to apply one formula first, then you get the R, and then you work backwards. So the pharmaceutical applications of contact angles. Wait, are you guys with me? Like, are you understanding? Does anyone have a question so far? Or are you okay? Okay. So pharmaceutical applications. So many pharmaceutical processes will involve interaction at interfaces described. So in all this, the contact angle and surface tension are important. Surface active agents are commonly employed in formulation as they reduce contact angle and hence aid in the wetting of a solid by reducing surface tension of L over V and also absorbing at the solid liquid interface and reducing. Okay, what this long sentence means to say is the lower the contact angle, the easier it is for the solid to get wet. So wetting is made easier if the contact angle is smaller. Yeah. So adsorption at liquid interfaces. So many compounds will have structures that contain two separate regions, a hydrophilic and a hydrophobic region. So a hydrophilic region is a water-loving region, and a hydrophobic region is the region which does not like water. So due to this dual structure, it's energetically favorable for these materials when dissolved to adsorb at interfaces. Let's scroll. What has happened? Sorry, guys, the person who's sharing the screen for me, Nikama, the internet has become a bit off. Does anyone else have the presentation? Where? Devani, they're in the group. They're under week 4.
Okay, wait, let me check.
They were shared by Diana, I think, in the morning. She forwarded them. So physical pharmaceutics week 4. I hearted them. So just go and see the ones which have lab hat.
Yeah, fine.
So yeah, we are at the adsorption at liquid interfaces. So what I said is that most compounds, they have two different regions, a hydrophilic and a hydrophobic region. So when dissolved, it's favorable for materials to absorb at interfaces, orienting themselves in. Oh, Devani is already sharing. It's okay. Yeah. Okay.
No, that's not me.
Okay, just share because whoever was sharing has stopped sharing.
I'll have to download. Give me a few minutes.
No, someone was already sharing. I don't know why they stopped. The one with the 4 zeros.
Zeros, yeah. I don't know them.
Okay, just scroll down. There. So orienting themselves in such a manner that the regions are associated with the appropriate solvent or air. Such materials are termed surface agents or surfactants. So pure liquid surfaces have a tendency to contract as a result of surface tension forces. So an example, again, I will go with water. So usually water, if it's like a pure liquid, it will have its own surface tension. But when you add let's say maybe powder to it on top of it, then the surface of the liquid is gonna contract a little bit because of the surface tension forces. So the packing of the surface with surface active molecules, it favors the expansion of the surface. So the surfactant molecules reduce surface tension of the liquid by an amount equal to the expanding pressure. So let's say your water, you put powder on it. So the powder works what it exerts some pressure on the surface of the liquid, yeah. So how the surface tension is reduced, it's gonna be the reduction of the surface tension of the water is gonna be proportional to the amount of tension or force that the powder applies on the surface of the liquid. Again, let me just repeat it. So you have your water, that is your liquid, and then you put some powder on it, yeah? So the powder will exert some pressure on the surface of the liquid, yeah? And this leads to a reduction in the surface tension. So how much the surface tension reduces is proportional to the amount of pressure that is exerted by that powder. So a surfactant lowers surface tension to different degrees. So an approximation, which is known as Straub's rule, states that for a particular homologous series of surfactants in a dilute solution, the concentration necessary to produce an equal lowering of surface tension decreases by a factor of 3 for each additional CH2 group. The formation of the adsorbed surface layer will not be instantaneous, but will be governed by the diffusion of the surfactant to the interface. So we go back to the powder. If you put your powder on the water, there's gonna be a layer that will be formed, but it's not formed instantly. So the surfactant must in which case I'm giving an example of the powder. The powder must exert pressure on the surface of the water, and it does that systematically, and it lowers it by a factor of 3 for each additional CH2 group. So if your powder has one CH2 group, then the surface tension decreases by a factor of 3. If you have one with two CH2 groups, then it will decrease by a factor of 6, and so on and so forth. And then it's done systematically. So the time taken to reach equilibrium depends on factors such as molecular size, shape, and the presence of impurities. So impurities will lower surface tension faster. For immiscible liquids, the reduction in interfacial tension may be such that emulsification takes place readily. So in certain cases, a negative adsorption may occur. So what this means is the solute molecules, they migrate away from the surface. Adsorption basically is when the what's it called, the surfactant is absorbed by the liquid to cause an interruption in the surface tension. So if these molecules, they migrate away from the surface, it means they are working vice versa, because usually the surfactants, they work to reduce surface tension. Yeah. So if the surfactants are on top and then they are moving away from the surface, then that is called negative adsorption. So in such cases, small increases in the surface tension will be observed. Are we together up to there? Basically, if I give a brief summary, I'm saying surfactants, they work to reduce surface tension, and the amount of surface tension reduced is proportional to the amount of pressure or tension that is applied by the surfactants. So in the case where there is negative adsorption, it means the solid molecules, the surfactants, they will migrate away from the surface, and this will cause an increase in surface tension. Was that like, are you guys understanding? Are you following me? Am I losing you? Mnaelewa ama? Simnijibu basi.
Tunaelewa. Kumbe vitu zilikuwa rahisi.
Okay. So the last part, I think, for this presentation is the surface excess concentration. So the extent of the distribution of a solute between an interface and the bulk phase is generally expressed in terms of the surface excess, which is given by N. So this is the amount of a material present at the interface in excess of that which would have been there if the bulk phase extended to the interface without a change in composition. That is quite a mouthful. So, what I'm understanding is a solute. The solvent is the liquid, a solute is the solid that you're putting into the solvent, yeah? So, there's the interface. So now let me use, I don't know which example to use. Just know there's an interface, yeah? So if when you're introducing, let me just go back. If you're introducing like a powder to water, the water is the liquid interface, there's the air interface as well. And then now the powder is trying to get into the water and to reduce surface tension and all that. So the material, the powder, which is present at the interface in excess, what would have been there if the bulk phase extended to the interface without a change in composition. So I don't know how to explain it in a way that makes sense. Basically, just to know there's an excess concentration of the surfactant, because the bulk of the interface would be the liquid. So if there was a way that the bulk phase can extend to the interface without a change in composition, then okay, just a moment. This is the amount in which I present. I'm not able to explain that sentence properly, but the surface excess concentration is where A is the area of the interface. The absorption of the material at any interface is given by Gibbs adsorption equation, which is expressed as that formula, which I can't even read. Yeah. D is the change in the interfacial tension. This is the surface excess concentration. And this is the chemical component of. Hey, guys, no, if I explain this, I will be lying to you. I'm not understanding even the formula. If someone knows how to do it, you can do it. This one, I'm not quite sure I can explain accurately. I hope it's not in PB paper. If it is, please let me know. I will start and go and look for extra information. So I will move on to the next one for the moment. It's really long. So this one I can explain. Monomolecular films, monolayers, because mono means one. So certain materials when dissolved in a suitable volatile solvent, they can be made to spread on the surface of the water to form one molecule thick. This may be regarded as an extreme case of adsorption, as all the molecules are at the surface. So surface excess concentrations can be calculated directly from knowledge of the amount of material and the surface area. The monolayer will reduce the surface tension of the water by an amount equal to the surface pressure. This one is like kind of like the way I was explaining the surfactants. So I don't know which one I should use, paraffin and water, even though might not be accurate. I just want to explain it. So if you put paraffin and water, assuming that the adhesive forces are stronger between paraffin and water, and then neither of them get saturated. So if it was a perfect scenario where the adhesive forces are stronger between them all the way through, we assume that the paraffin will form one layer all over the water, the surface of the water. And this will cause, obviously, it will cause a reduction in surface tension. And this reduction in surface tension is going to be equal to the surface pressure. So whatever tension, whatever pressure is applied by the layer of the paraffin on the water, that is also gonna be the equal amount of surface tension reduced. So the amount of pressure applied by the paraffin is gonna be equal to the amount of surface tension reduced. They are proportional. That's what I mean to say. So the surface pressure, which is the expanding pressure due to the monolayer opposing the contracting of the water, can be measured directly by enclosing the film between movable barriers. So this is the formula that we can use to calculate, where pi is the surface pressure, YO is the surface tension of the clean liquid, which will probably be the paraffin in that I'm trying to say would be the liquid that covers the water. And then the YM is going to be the liquid covered with the monolayer. In my example, that is the water, because water is what is going to be covered by paraffin. Paraffin will be the monolayer. So monolayers exist in different physical states, which are some way analogous to the three states of matter, which are solid, liquid, and gas. Pharmaceutically, the monolayers have been used to study polymers, which are used for film coating and packages, and as models for cell membranes. So for film coating, it's more of like you have your tablet, which basically has powders which are compacted, and then the powders you pour liquid that will form the coat. So we are moving on the assumption, or when they are coating, it's like the liquid that is being used to coat the tablet or the powders which have been compacted should have the adhesive forces should be very strong between them, such that even when the tablets are in the machine and you're pouring the liquid, they're gonna form a monolayer. I think we also that in the industry, where you'd see like there was white tablets and then there's a pink liquid and then the tablets turn pink and they're being coated. Yeah, that's how I can explain that. So yeah, if there's no question, I'm done with that, the first presentation. Are you guys okay? Do you have a question, a comment? Muongeleshe watu, acheni kuwa warude. Haya, sawa. I guess if there's no question, then we can move to the next week. Or wait, should we take a break? You guys wanna take a break, like a 5 minute or 10 minute break before we start? Hey, hata hiyo mtajibu.
We can start at 8
At
for
8?
for the second session.
Okay. Start on the next one.
In this video, we will see how surfactants reduce surface tension. First, we will study structure of surfactant molecule. Then we will quickly see surface tension. And then we will see mechanism of action of surfactants. Let's get started. First, let's see structure of surfactant molecule. Surfactants are lipids or proteins. Their general structure is like this. They have a head and a tail. The head has charged atoms. Due to this, it dissolves in water, or in other words, it's hydrophilic. The tail, on the other hand, do not have any charged moiety, so it is hydrophobic. This was about the structure. Now let's quickly revise what we have seen in video on surface tension. We saw that water molecules attract each other. Molecules deep inside the bulk are attracted equally in all the directions, so there is no net force acting on them. However, water molecules on the surface do not have any other water molecules upward to pull them. So they experience net pull downwards by water molecules in the bulk. As they dive deep, the water molecules that stay on the surface develop surface tension. This is how surface tension develops. The key point that I want you to focus here is this downward pull on the surface molecules. It's this pull that's causing surface tension. Now let's throw a surfactant molecule in water. In this molecule, this head is hydrophilic, so it wants to stay with water. However, this tail is hydrophobic, so it wants to stay away from water. One solution to make both of them happy is this orientation at the surface. Say this water-soluble head is in contact with water. Due to the charged moiety, it is attracted by surrounding water molecules. The tail is out of water in the air phase. As it's hydrophobic, it pulls the surfactant molecules upward away from the water. All these forces balance each other. So there is no net force acting on the molecule and it stays on the surface. But how does it reduce surface tension? 1. As it occupies area on the surface, density of water molecules on the surface decreases. The lesser the water molecules on the surface, the lesser the surface tension. Second, the head portion of the surfactant molecule attracts the water molecules near the surface. This attraction opposes the downward pull on these water molecules. Here, surfactant molecule is prevented from going deep by hydrophobic tail. Now look at the downward pull on these surface molecules. It's lesser as compared to that without surfactant. Thus, surfactant reduces tendency of surface molecules to dive deep in the bulk water. This results in reduced surface tension. The more the surfactant molecules on the surface, the less the surface tension. I hope now it's clear how surfactants work. We will see specific problems solved by surfactants in a separate video. If you struggle understanding medical concepts, subscribe to the channel and also follow me at other platforms. At nonstopneuron.com, learning medical concepts is as
Saru, you can continue.
You can start?
I-
Okay.
Yeah, I finished.
The video. Okay, so like the video was showing, surfactant. These are substances, which part of their molecule is lipophilic and part of it is hydrophilic. So it just means one of them is attracted to water and one of them is attracted to what is it? Fatty things. Yeah. So when dispersed in the bulk of liquids, they move on their own to the surface or the interfaces in the liquid where they lower the surface or interfacial tension. Although amphiphilic, the surface active agents can be predominantly hydrophilic or lipophilic, depending on the kind and number of groups on the molecule. So obviously, if the molecule has more lipophilic groups, it means it's gonna move more to the lipophilic part, yeah. And if it has more hydrophilic group, then automatically more of it will move to the hydrophilic part. So upon dispersion in water, surfactants relocate the surfaces. The hydrophilic, which is the polar part, will be the water, and the lipophilic part will stick out of the surface of the water. Because it is hydrophilic, obviously, it won't the lipophilic part cannot enter the hydrophilic part because they are polar opposites. I hope it's making sense. So in the case of a water-oil interface, the polar part will obviously be on the water side, and while the lipophilic part will be on the oil interface. Okay? So when the surfactant molecules saturate the surface of the water, they form micelles in the bulk of the water. So basically, if so let's say we've said the surfactant has got a lipophilic part and a hydrophilic part. So when the hydrophilic part saturates it enters the water and it gets saturated, then now there's gonna be a formation of micelles, and the formation of the micelles will be formed in the bulk of the water. So the bulk of the water is basically just the water part. So the micelles are usually aggregates of about 50 or more surface active molecules, which are also known as surfactants. Okay. So in what I've said is in water oil water oil ratio. When you have surfactants, the hydrophilic part will go to the water, and then when it's saturated, it's gonna form micelles, which will be in the bulk of the water. So HLB value and interaction of surfactants. So HLB is the hydrophilic lipophilic balance. Like we've said, there's surfactants, there's a hydrophilic part, and there's also a lipophilic part. So HLB will be the number that describes the hydrophilic lipophilic nature of a surface active molecule. So basically it explains whether the surface active molecule or surfactant has more hydrophilic groups or lipophilic groups. So it's an arbitrary scale which was developed to organize information about the surfactants. So there are different formulas that are used to calculate HLB value, and this is one of the examples. So it just shows the summation of the hydrophilic groups minus the summation of the lipophilic groups plus 7. That will be the HLB values. So surfactants which have a HLB value less than 9 means they are lipophilic, which means more of these surfactants are going to be attracted to, if there was a water-oil interface, most of it will go into the oil. The smaller the HLB value, the more lipophilic the character. So 9 and below. So the lower you go, it means the more you add the number of lipophilic groups. A surfactant with a HLB value less than 9 forms water oil emulsions. Okay? I hope you are getting to that. Is that making sense, guys? Is it?
Yes.
Okay. So it will form water oil emulsions because the water is at the top, the oil is at the bottom, because oil is heavier than water, I'm assuming. So it means most of the surfactants are gonna break the surface, and then most of them are gonna settle at the oil part because the molecule in question has got more of the lipophilic groups. So it will form a water oil emulsion. So a HLB value of less than 6 signifies an oil-soluble surfactant. Those in the range of 1 to 3 are used as antifoaming agents. So surfactants with the HLB value above 9, then obviously it will be vice versa because it means they will be hydrophilic, which means they're going to form oil-water emulsions because most of them, this surfactant is going to be hydrophilic and it's going to go to the water side because water and hydrophilic parts of the surfactant are what are going to be attracted together. So the higher the HLB value, the more the hydrophilic character. So it's basically vice versa. If you can get one concept, the other one is the opposite. So the HLB value required for emulsification of a particular oil in a water emulsion can be determined by mixing different combinations of the surfactants until you form optimum and stable emulsion. So the combination of surfactants, we will have a new HLB value, which will be the HLB mixture, and it's going to be expressed as HLB mixture is equals to F HLB1 plus 1 minus F HLB2, where F is the fraction of surfactant 1 and 1 minus F is the fraction of the second surfactant. So you can classify your surfactants. The same surfactants which have got a hydrophilic group and a lipophilic group. So the first classification will be anionic surface active agents. And ions, I think they had a negative value. So the surface active portion of an anionic surfactant has a negative charge. Yeah. So an example will be the sodium lauryl sulfate. So these ones are used in pharmaceutical and cosmetic industries. They have an unpleasant smell, unpleasant taste, and the skin irritation potential. So if you want to remember what's anionic, just a moment, excuse me, guys. Okay, sorry. So what I was saying is if you want to remember, like if maybe in a question it says the surface the surfactants, they have a pleasant taste and skin irritation potential, you know it's the anionic surfactants. So they're not compatible with the cationic surface active agents, but are compatible with non-ionics and Zwitter ionic surfactants. I do not remember what Zwitter ions were. I don't know if anyone remembers. If anyone remembers, you can write it in the chat. So the types of anionic surfactants would be, yes, sodium and potassium salts of straight chain fatty acids, which are soaps, sulfates, sulfonates, and N-acyl taurines. These ones have good skin compatibility, exhibiting stability over a wide range of pH. So soaps, sulfates, sulfonates, and N-acyl taurines are all anionic surfactants, which means they all have negative charges. And then there's the next one would be the cationic surface active agents. So this one's obviously cations have positive charges. So then I see you can scroll. Okay, so the surface active portion of a cationic surfactant has a positive charge. You can just know that because cations always have positive charges. An example is dodecyl ammonium chloride. So they can be used as bactericidals. They absorb onto the negatively charged surfaces, so they can also be used as hair conditioners and fabric softeners. So the cationic surfactants are incompatible with anionic surfactants, but they are compatible with non-ionics and zwitterionics. So the anionic surfactants, the ones that were up there, we said they are incompatible with non-ionics. They're also incompatible with zwitterionics. Just scroll up to confirm. Oh wait, it's vice versa. So the cationic ones, the anionic ones, they are incompatible with the cationic ones, obviously because they have opposite charges, but they are compatible with non-ionics and zwitterionics. And then the cationic surfactants are also incompatible with the anionic, but they're compatible with non-ionics and zwitterionics. So both of them are compatible with zwitterionics and non-ionics. They're just not compatible with each other. I hope I'm not confused anyone. So quaternary ammonium compounds are among the most utilized cationic surfactants. So the examples of surfactants will include alkyl benzyl dimethyl ammonium salts, such as germicides, which makes sense because we said it can be used as a bactericidal. So then after that, we have non-ionic. So we've done cationic, we've done anionic, and now we are doing non-ionic. So these ones are not electrolytes, and their surface active portion has no charge. Okay, so they are not affected by the presence of salt or changes in pH because, again, they have no charges. The hydrophilic group may contain hydroxyl groups, polyoxyethylene groups, or saccharides. So the types of non-ionic surfactants will include these ones: fatty acids, sorbitol, and polyxylethylene sorbitol. Okay, that's a very long word. So the next one are zwitterionic surface active agents. So far we've done anionic, which have negative charges, cationic, which have positive charges, non-ionic, which have got no charges, and now we're in the zwitterionic. So these ones are compatible with all types of surface active agents, surfactants, which is why we say the cationic, they're incompatible with the anionic, but they're compatible with non-ionic, and they're compatible with zwitterionic. And then the anionic, they're not compatible with the cationic, but they're compatible with both non-ionic and zwitterionic. And then clearly also the non-ionic are compatible with zwitterionic. So zwitterionic would be probably the best surface active agents because they're compatible with all other surface active agents. So depending on pH of the medium they are in, they can be anionic, cationic, or zwitterionic. Their main use is as co-surfactants to boost the forming properties of the other surfactants, which is why probably they are compatible with all different types of surfactants. So they can change their charge based on the pH or the medium that they are in. So they can have negative charges, they can have positive charges, and they can have no charges at all. Okay, so let's scroll down. So when it comes to the application of the knowledge of the surface film behavior, because we've talked about now the surface tension, how it's changed, we've talked about surfactants. So now we're trying to apply that knowledge. So while the surface active substances, they stay preferentially at the surface of the liquid to which they're added and lower the surface tension, like we've kept saying. Surface inactive substances, when added to a liquid, concentrate in the bulk of the liquid and increase its surface tension. So this is the opposite of what surfactants do. Okay, surface inactive substances will work to increase the surface tension because they concentrate in the bulk of the liquid. However, surfactants will concentrate on the surface of the liquid, and this causes them to lower surface tension. So surface tension decreases with increasing concentration of the surfactant. However, at a certain concentration, the surface tension stops decreasing and reaches a plateau. So the table over there shows it, yeah? So it's like when you introduce an impurity, example, like a powder on water, so the more it's adsorbed, the more it exerts pressure, the more it reduces surface tension proportionally. But at some point, once it gets saturated, it will reach a plateau. So this is this over here is the plateau, and I think at that plateau is where it's maximally concentrated. So this concentration is called critical micelle concentration. This is because at this concentration, the surface is saturated with surface active molecules that I had explained. So even if you increase the concentration, it's not going to decrease the surface tension. Instead, it will form micelles in the bulk to protect the hydrophobic groups from the aqueous environment. Because again, we said the film is being formed because the adhesive forces are stronger between the, like now the powder and the water, they have stronger adhesive forces. So after it has formed, after it has affected the surface tension, it has been adsorbed to its maximally. We go back to the fact that the powder also has got hydrophobic groups which don't mix with water. So it's gonna form micelles to protect the hydrophobic parts. So the concentration at the surface active agent also affects other properties of the solution as illustrated. So it affects the interfacial tension and also it affects osmotic pressure. So interfacial tension will decrease. Again, like when you add a surfactant, it exerts pressure, it decreases the surface tension, and it also decreases the interfacial tension. There was a formula in the morning that I explained where interfacial tension as well as surface tension, they are proportional, they have the same numerical value. So osmotic pressure, on the other hand, goes increasing. So it's the opposite of the interfacial tension and the surface tension. Drug solubility will increase when you put the surfactants, and then detergency, I'm not sure what detergency is. Okay, so you can scroll. So adsorption at solid interfaces. So this whole time I've been explaining from the perception where you put a solid on top of a liquid, because I was explaining the wetting phenomena and the process of adsorption. So adsorption can also occur at solid surfaces. So that's what we're going to go ahead and do right now. So if a gas or vapor is brought into contact with a solid, some of it becomes attached to the surface of the solid. So this will reduce the imbalance of attractive forces and hence the surface free energy. So adsorption is the process by which a molecule binds to the surface of a substrate. So the molecule that is binding is called the adsorbate, and then the solid in which the molecule is binding is called the adsorbent. So adsorption may be relatively weak, non-specific forces, which are van der Waals forces, being termed by physical adsorption. Alternatively, it could be also stronger specific valence forces called chemisorption. Physical absorption is rapid and reversible, and multi-layer adsorption is possible. Chemisorption, which we've said is the stronger specific valence forces. It's specific, it requires activation energy, and therefore may be slow and not readily reversible. I think this takes me back to the valence electrons when we learned in the first 2 sessions when Jambi was teaching us. I think it uses the same mechanism or explanation where the valence electrons are more closely tied to the nucleus, it's harder to remove them and all that. So adsorption, which is happening like the chemisorption, which includes valence forces might be more difficult compared to the van der Waals forces, which are weak non-specific forces. So only monomolecular chemisorb layer are possible. So physical absorption, example is they are the relatively non-weak, non-specific forces. Just think van der Waals forces, they're not very strong. Chemisorption, it's the valence forces, which is going to be stronger, which means there's an activation energy needed, which means it's slower and it's not really reversible. However, the one with the van der Waals forces, it's easier and it's easier to reverse because you don't need to activate and you don't use more energy. So yeah, so adsorption studies generally involve the determination of the amount of gas or vapor that is adsorbed by a given mass at constant temperature. Okay, so you have a gas that is being adsorbed by a solid, so you're just trying to see the amount of vapor that will be absorbed by this mass, the constant temperature. So the determinations are carried out at different equilibrium pressures, and the pressure attained after absorption has taken place to yield the adsorption isotherm. So they're gonna basically, to determine it, you're gonna have different equilibrium pressures, and then they just defined into brackets equilibrium pressures are the pressures attained after the adsorption has taken place. So the isotherms obtained can generally be classified into 5 types. So type 1, these isotherms, they exhibit a rapid increase in absorption up to a limiting value. They are referred to as the Langmuir type isotherms and are due to the absorption be restricted to a monolayer. So the adsorption of the chemisorption type will give this type of curve. So the way we said there's a rapid rise in absorption up to a limiting value. It's like it's rapidly absorbed until it reaches this place and then it plateaus. That's the type 1. And then the type 2 isotherms represent multi-layer physical absorption on non-porous materials. So the first one is going to be a monolayer and it's going to be rapid and then it's going to plateau at some point. The type 2, it's like it goes up and then it plateaus and then after a while it still goes up again. So yeah, the difference between type 1 and type 2 is like the type 2, there can be multiple layers, but in type 1 it's a monolayer. And then type 3 and 4, they occur when the adsorption of the first layer is weak and they are rare. That's the only example given. Type 3 and 5. So the adsorption in the first layer is weak and rare. So the first one, it's a monolayer, it's rapid, it plateaus. The second one can form multi-layers, it plateaus a bit, then it keeps going up. Then types 3 and 5 occur when the adsorption of the first layer is weak. And then type 4 is considered to be due to the condensation of vapor in fine capillaries within a porous solid. The graph, it looks similar to the type 2 one. So the difference would be the type 2 one, it's a multi-layered one here on non-porous materials, and the type 4 is within a porous solid. Okay, so just let me summarize. So the first one is rapid, forms a monolayer, and then it plateaus. The second one, it's a multi-layer, so it goes up, then it plateaus, then it goes up again. And then the third one and the fifth one, they occur when the absorption of the first layer is weak and they're rare. And then the fourth one is similar to the second one in the curve, but the difference is the absorption happens within a porous solid. Okay? Everyone is still with me up to there? Hopefully. Okay, let's scroll. So several equations have been developed to fit the experimentally observed isotherm. So the Langmuir adsorption isotherm. That's the first one. The equation was derived by assuming that only monolayer coverage was possible. Hence, it's only applicable to type 1 isotherms, like I was saying. And this is the equation that you use. Pm over x is equals to 1 over bp plus 1 over ab, where p, m, x are defined previously, and b and a are constant. Where b as a constant is the amount of gas required to produce a monolayer, and so hence plotting PMLX against P should give a straight line with a slope IB and intercept 1AB. So basically just go back to the graph. That is what I'm trying to explain. Then the second one is the Freundlich adsorption isotherm. This is given as x over m, kp 1 over n. Where n and k are constant, this equation does not predict a limiting value, as does the Langmuir equation. So this Freundlich adsorption isotherm, I think it would represent the isotherm type 2 and type 4, because you can see it goes, it plateaus, then it keeps going up. So there's no limiting value as per the graphs. If you go back to the graphs up there, you'll see like it just kept going. Yeah, it kept going up. Like there was no specific plateau for the type 2 and the type 4. You see it goes, then at some point it plateaus a bit, then it keeps going up. So yeah. And then the other one is the oh, actually that's it. So the Brownier, Emmett, and Taylor equation. So this equation takes into account the multi-layer adsorption and so describes the type 2 isotherms. So sorry, I was wrong. I thought the second equation also represented the type 2, but I was wrong. So this equation takes into account the multi-layer adsorption and so describes type 2 isotherms. All right, maybe the type 2 isotherms can be described by more than one equation, because I feel like the second equation also describes the type 2 isotherms. So the equation reduces to the Langmuir equation if absorption is restricted to a monolayer formation. Okay, so it describes the type 2 isotherms because it's the multi-layer adsorption. From everything that we've explained, the only one with the multi-layer adsorption is the type 2 isotherms. However, the equation can be reduced to the Langmuir equation if adsorption is restricted to a monolayer formation. So then there's the last part is the solid liquid systems. So the adsorption of most interest is that of a solute in solution onto a solid. Ati nini? Solid liquid system. The adsorption of most interest is that of a solute in solution onto a solid. So I thought a solute is a solid also. Can someone explain, does someone understand that sentence? Diana, do you understand that sentence? The first one.
Nataka
Okay.
kusema hiyo solid kwa maji inakuwa absorbed onto a solid phase, like imedissolve already but sasa inataka kuabsorbiwa into a solid phase or a solid
Oh, thank you. So the equations most widely used to interpret the data are those of the Langmuir and the Freundlich equations. So the pressure terms are replaced by
something I don't.
The pressure terms are replaced by the concentration terms. So basically, you're gonna have to go back to the formula for these different expressions, and then you're just gonna have to, when you input them, you're gonna find the final formula. So several factors will affect the extent of absorption from the solution. These include the following: solid concentration. So an increase in the concentration of the solid will cause an increase in the amount of absorption that occurs at equilibrium until a limiting value is reached. I think the limiting value is where it becomes saturated. And then the temperature, adsorption is generally exothermic, and hence increase in temperature leads to decrease in absorption. So exothermic are the ones which give out temperature, yeah. The processes which there's the output, they give out heat. So it's exothermic, so an increase in temperature leads to a decrease in absorption. And then pH, influence of pH is usually through a change in the ionization of the solute, and the influence will depend on which species is more strongly absorbed. So it's not straightforward. It depends on what you have, the change in the ionization, and then it depends on which species is more strongly absorbed. So the surface area of the absorbent, an increased surface area achieved by a reduction in particle size will increase the extent of absorption. This makes sense when you think about how when in powders, when you reduce the particle size of the powders, or when you make it more, what's it called, compact, it means you're gonna increase the surface area and you're gonna reduce the size, so it makes the powder more likely to be absorbed in water or liquid, if I remember correctly from what Calvin was teaching us. And so finally, we have the pharmaceutical applications of adsorption from solution. So it's of most interest in chromatographic techniques and the removal of unwanted materials. So materials such as activated charcoal can be given in cases of orally taken poisons to adsorb the toxic materials. So these adsorbents may also be used in hemodialysis to remove the products of dialysis from the dialyzing solution, allowing the solution to be recycled. Oh, that's really nice. So adsorption may cause problems in formulation where drugs or other materials such as preservatives are adsorbed by the containers, which means it can also cause a disadvantage because this will reduce the effective concentration. And then in addition, certain additives such as parabens may be adsorbed into the solid material present in a suspension, leading to loss of antimicrobial activity. So it has both a positive side and a negative side. Positive is it can remove toxins, and then it can also be used to remove the adsorbents that are used to remove the products of dialysis, so you can reuse the solution. But also it can bring a problem where preservatives and drug materials can be adsorbed from containers and reducing the effectiveness. And also it can adsorb parabens, which can lead to the loss in antimicrobial activity. Yeah, does anyone have a question about anything? Okay, if there's no question, thank you for listening. Yeah.
Okay, thank you, Saru. Thank you so much. I think, is it okay with everyone? Should we continue or we continue tomorrow in the morning? We do a recap of what Saru has covered, then plus what Hiral will cover tomorrow in the morning.
Then I won't be able to do in the morning, so I can just do
So
the
you,
electric
now.
double layer because it's short.
Okay, so.
Electrochemical around a particle is explained as follows. If a particle of a size greater than 1 nanometer is dispersed in water, there will be a reaction at the solid-liquid interface. Both parts, the solid and the liquid part, carry different energy levels, which lead to a tension at their interface once they get into close contact. Basically, All substances intrinsically carry a negative surface charge once they are dispersed in water. This is caused by the high dielectric constant of water. Generally speaking, media with a lower dielectric constant carry an anionic surface charge. Water contains ions of dissolved salts. Attracted by the surface charge, these ions gather around the particle. A well-ordered and immovable layer covers the surface of the particle like a skin. This layer is also called the stationary layer, or Stern layer. Cationic ions neutralize the anionic surface charge. However, as ions are often surrounded by water molecules, they are rather big and cannot neutralize the surface charge completely. A residual anionic charge remains. This remaining anionic charge attracts further ions from the surrounding water, so that a second layer develops around the particle. This layer is further away from the particle's surface. The attractive force of the anionic charges get weaker with the distance, and therefore this second layer is less ordered and movable. The second layer is called diffuse layer or Gouy-Chapman layer, and is colloquially often termed cloud of counterions. The boundary line between the stationary and the diffuse ions is a shear plane. The potential at this boundary line is called Stern potential or streaming potential. If the diffuse ions are displaced from the particle they surround, a potential difference is created and can be measured.
What happens when a charged particle is immersed in a liquid, such as an aqueous electrolyte solution? In this case, there's a positively charged particle surface, and somewhere there has to be a balancing negative charge. Typically,
Yeah, so like from the video, we saw that when you when a particle comes in contact with like an aqueous medium, there's always like, because of the surface electric charge on the particle and the charges in the aqueous medium, there'll be some attraction between the particles and the aqueous medium. So there's some mechanisms for this. So the first one is ion dissolution, where ionic substances can acquire a surface charge. So that's like now the particle, and now the aqueous medium. It's not a must that it only has one type of charge, but it will have different charges, either positive or like both positive and negative. Then ionization, where the charge is controlled by the surface groupings. And the third one is ion adsorption, where the net charge is acquired by unequal adsorption of oppositely charged ions. Then how for the electric double layer, the solid particle comes in contact with the solution where it has both positive and negative charges, like I said before. And then mostly the surface the surface charge of the particle is usually negative, like let's say it's negative, right? So the one that, if it's negative, then the positively charged particles, no, the positive charges on in the aqueous medium is called the counter ions, while the oppositely charged or the like charge is called co-ions. So that will repel the surface. So counter ions will get attracted to the surface of the particles, and co-ions are repelled from the surface. Just go down. Yeah, so when you shake it or you agitate that mixture, it will tend to redisperse the ions in the solution, which now results in an electrical double layer. Yeah. Yeah, the electrical double layer, and it's made up of the charged surface and a neutralizing excess of the counter ions over the co-ions. So what happens, just a minute. Yeah, so from the video, like we saw that the double layer has two parts. It's the inner layer, which is that stern layer, and then now the other part, which is the diffuse part where the other ions are distributed. And the two parts of the double layer are separated by a stern plane. So there is the stern layer, and then in between the stern layer and the diffuse layer, or the diffuse part, is the stern plane. So if you go down, there's a diagram which is better. Yeah, this one. So on the surface, you'll have now the stern layer, and then the stern plane. Yeah, and then the other part is the diffuse part, which is not shown on the diagram. So what happens in this when these like potential changes with this double layer? So what happens is that the potential changes linearly from the surface potential, which is from now the solid surface, to the stern layer, which is the stern potential. It's linear, but once you go further away from that stern layer, that potential, like, it reduces to zero, like, but it goes exponentially. So it's linear at first and then exponential, and it goes to zero once you move away from the stern layer. Yeah, that. Okay, and then there is another layer, or another plane, which is now termed the surface, or a plane of shear, which represents the boundary of relative movement between the solid and the liquid. So when you go to the diagram, it shows the plane of shear, which is now in between the stern plane and the diffuse part. So that is now the solvating. It's basically the solvating layer. And then this plane of shear is now termed zeta. So it measures the zeta potential of that solution. So when we're talking in terms of like how it's applied in pharmaceutics, this zeta potential or just electric double layer, you have to think about when you have the stability of a solution, or like an emulsion or something, will increase when they have like charges, because they will repel each other, like the particles will repel each other. That is good stability when it repels each other. When it gets attracted, that's when it's not stable, because if they have if they have oppositely charged charges, then they will get attracted and form agglomerates. So basically you need like charges to repel the solid particles, to give a good stability of the solution, or whichever formulation that has those dispersed particles. Yeah, that's it for electric double layer. And then for zeta potential, it measures the stability of the colloidal. Again, like it has to be either positive or negative. So yeah, I'm not really sure about the zeta potential, but I know it basically looks at the stability of the colloidal solution or the particles. Yeah. I think we're done for today.
Yes, thank you, Hiral. I think we'll do a recap of everything in the morning session before we go to the next part.